Okay, now we're streaming. So yes, welcome back. Little did you know, and little did I know, that you are actually signing up for an online class this semester. This is unprecedented, everyone around me says. But yeah, it's our 5th class in a row online. Thank you for your patience in making this work. It's a lovely day outside, isn't it? Whiteout conditions, it's super. So hopefully you all are somewhere safe, somewhere warm, or can get back there as soon as possible, as it were. I just a few minutes ago put up homework 2 in terms of making it available as part of your point totals. If you have questions about why you missed what you did, please let me know. Not everyone has finished it yet, so we can't go over it in class. Once everyone's done, we can go over these things. But until then, you'll have to let me know on an individual basis if there's any of that you want to go over in terms of your wrong answers. We'll have a quiz next time because we haven't covered everything that we need to be able to finish it. So that we'll go over that right at the beginning of class on Thursday, which may be in person, but I'm told there is yet another snowstorm coming, so maybe not. We'll see. So any questions or any logistical things you want to ask about before we get going? No? We're good? All right. Then let's see here. Tell me what you remember from last time. You can use the chat window. You can use your voices. No one remembers anything? I lost my chat window. Hang on. Here's a chat. Haha, thank you, Kofungi says. I didn't come last time, so yes, you are off the hook. But everyone else. Do you remember anything from last time? Maybe a new letter? Maybe a new kind of error term? No? Okay, do we need to go back over it then? Would that be helpful? Do some reviewing? Alright, I've lost my meeting control window. Where did it go? Just a second. I need to stop the share so I can get this back. Here we go. There, now I can see everybody again. Alright, and there, we'll share the screen again. There we go. Okay, let's go back and review then. So let's look at lecture 3. My phone is buzzing at me, sorry. Make that stop. Okay, so I have this open at the end. We'll review back at the top here. So what we talked about last time was changing the model for the variance to be better suited for longitudinal data. So we started with slide 2 here, talking about general linear models, which have one error term, this E at the end, and the reason that it's okay that they have one error term is that there's only one dimension of sampling. If each person has one outcome, then the only type of variation there can be is differences between persons. So that's why I think of this as a between-person type of model. If each person contributes more than one outcome, which is the case in longitudinal data, or more generally what we would refer to as multivariate data, more than one outcome, it could be over time or it could be different conditions, what have you, then we have 2 different kinds of variation that's possible. We have within-person variation across the outcomes, so time, occasions in this case, and between persons. So we need to extend the model to be able to address both types of variation simultaneously. And so that was where we got to this idea that we have differences between people in their means over time as one type of variability. That's the between. And then differences within persons around their means, and that is the within. So if we put that into a picture, it'll look something like this here. The total variability at each occasion is the same. What we're doing is partitioning it into two different sources. U0I is the source of variation that represents between person mean differences. So each person's U is the deviation from the grand mean to their person mean. So in this case, because this purple person on slide 10 is lower than everybody else, their U would be negative. If somebody was doing better than everyone else, their U would be positive. And in terms of the notation, it's U0I, U0 because it's an intercept, so it maps onto beta 0, and it gets an I because each person gets their own. So once each person gets their own U0, by which they get their own person mean, E is what's left. So that's the remaining distance between a person's outcome and that predicted by their person mean. And so the idea then is that U0I is in the model to build in dependency, to build in correlation. U0 is why the E's from the same person would have been related, because they're all below the mean. Once we factor in that U0 below the mean tendency, the E's are supposed to be to meet the same type of assumptions we would say in a general linear model: independent, constant variance, and normal in this case, although we can change the latter with different types of generalized models. So to put it into equations then, what we're talking about is starting from a different place. An empty model, term we talked about last week, means no predictors. So these two models on slide 12 have the same model for the means. They both have only a fixed intercept. Fixed is the part that everybody gets. That's beta 0 in this notation. Where they differ is in their model for the variance, where the within person model, and I have a plus within on here to indicate that it's adding to the between person, adds that U0 so that each person gets their own mean. And so it allows the total variation to be split into how much is because of person mean differences, because of this U0I variance across people, and how much is within person variation over time. And so then the very first thing we want to figure out is something called an interclass correlation, which is the ratio of how much of the total variability is because of this random intercept. So just to review the terminology here, this is slide 11. Total variability gets partitioned into two sources. Level 2 is between person, is inter-individual differences, is because people have different means, and more specifically in this case that's random intercept variance. That's what it's going to be called. Level 2 is all kinds of between person differences. Right now there's only one, just an intercept. Later on there will be slope differences as well. Level 1 then is within person. It's the longitudinal part, or intra-individual differences, and that's the variability around the person mean, so that's the E variance. So level 2, random intercept, level 1, residual instead. The amount of the total variability on the bottom here in this interclass correlation formula relative to the top, which is level 2, is this interclass correlation. So you can think of this two different ways. One is that it's just the proportion of variation that is due to the level 2 between person random intercept variance. Or you can think of it as the average correlation across occasions from the same person. It's the same thing, but either way, it's an effect size. I will show you today how we can test for whether or not this model, this within person model on the bottom here, fits significantly better than the between person model. And more generally, we can test any model for the variance. But that significance test doesn't give you a sense of how prevalent the intercept variance is. Whether it's greater than 0 is going to be largely a factor of sample size. Just how big it is in an absolute sense is the effect size given by the interclass correlation. So, okay, how are we doing so far? Any questions?
May I ask a quick question?
Please do.
So, like in the blue box, we have the arm matrix or the correlation matrix.
Mm-hmm.
So is that the dimension of that is like if we have 3%, we have 3 by 3. We have
It
more
the R matrix is the dimensions. I'll go with the number of occasions.
number. Oh, occasion. Oh, yeah.
Yep.
Oh, okay.
Yep.
Yeah.
So the diagonal is the variation across persons at each occasion.
Oh, yeah.
Yeah, so each person is going to get their own R matrix in terms of the amount of data they're contributing. So everybody's R matrix would be a 3 by 3 if everybody had 3 occasions.
3 occasion. Oh, yes, that makes sense. Yeah.
Mm-hmm. But if
Yep.
like somebody only has 2, their R matrix would be the 2 by 2.
2 by 2.
Mm-hmm.
Yeah.
So
Okay.
it's person specific in terms of the dimensions, but we assume that the contents of it are the same. So what this R matrix is saying is that the total variability at any one occasion, so note that the diagonal is equal, is part because of within person level 1 E variance and part because of between person level 2 U0 variance.
Yeah.
And the only reason for covariance, so the off diagonals here are all the same, they are irrespective of time. The only reason for covariance here is because of the random intercept. Because some people start out higher than others, the occasions are correlated, and that's the only reason. That's what this model says. That's a pretty strict assumption, but that's our jumping off point.
Thank you.
You are welcome. Other questions? So we looked at an example, which I will just summarize briefly here. And what ended up happening is that the significance tests for the time effect in the example, the within-person effect, as well as the group by time interaction, those significance tests ended up using just the within-person residual variance to form their standard errors, whereas the between effect, the group effect, used all of the variations. So we ended up with a different result after we partitioned the variance and used only the relevant variance in testing each effect. So that was the point of that example, and it was also to show you why we can't just have 2 occasions. Because the error term in a model like this is the same thing as saying there's a person by time interaction when you only have 2 occasions. So you can either say that people change differently and that you've perfectly captured everyone's rate of change. That's the right-hand side. Or you can say people change the same and there's some residual variability. You cannot distinguish those 2 interpretations. The left-hand side seems more plausible than perfection. So that's why we need 3 occasions to be able to say how much of the variability over time is because some people change differently versus residual error for unknown reasons. And I think that was about where we left off. So, anything else that I can clarify or review before we move on? That's a no. Let's see, where are my people? Here's my people. Okay. All right, so I'm going to pick on James. Are you there, James?
Yep, I'm here.
Okay, do you know why I'm going to pick on you?
No, I don't know.
I shouldn't say pick on. I'm going to ask you a question that I think I know the answer to. It's because you're from psychology, right?
Yes.
I'm from psychology. No one would ever trust me to be an actual psychologist, but that is technically what my PhD is in.
I think that'll be true for me too.
Yeah, I don't do therapy, although ironically I got into the profession. I was one of those undergraduate psychology majors who wanted to help people. And I figured out pretty quickly that I did not want to help people in the traditional way, but I still help people. I just help them with their data. So, it's a different kind of therapy, really, but I digress. So in the world of psychology, ANOVA was like the bread and butter. It was all about experimental design or quasi-experimental design, and everything was an ANOVA of some kind. Is it still that way in your world over there in psychology?
I guess in the other coursework, we are trying to break down the barriers between ANOVA and regression, and we're starting to see it as more of a unitary framework.
Mm-hmm.
So similar to the way that you're teaching it.
Yeah, that's been a long time coming. It's not like this is a new concept. I think there was an article by Cohen in like 1950 that was like, "Hey, this is just the GLM. These aren't different." But that doesn't that type of thinking hasn't always permeated the way that people talk about it in classes. Like people have a regression class or an ANOVA class, and repeated measures ANOVA in particular was much beloved in my psychology training. Is that something that you guys get a lot of exposure to? Or not so much?
I've gotten some exposure.
Some. Okay, so I did not understand that there was more than one kind of repeated measures ANOVA. I only thought there was one kind for the longest time, and it blew my mind to find out that there was another kind. So it turns out that these repeated measures ANOVA variants are going to be important special cases of more general longitudinal modeling. So I wanted to go over how those models look in this framework, what they assume, what they don't assume, because I've found that people who are trained in repeated measures ANOVA sometimes are inherently suspicious of mixed models because they don't understand how they relate when they're the same and when they're different. So I'm done picking on you now. See, if you don't have the same like repeated measures ANOVA is the only way type of training that I went through, then I don't have to try and convince you otherwise. So clearly I don't, because you're here, right? So,
yes.
Yes, and so other folks who are from the EMS program, did you get repeated measures ANOVA as part of your coursework? No one's talking. Can you type if you can't talk? I gotta find my little chat window again. There's one.
Not in this way.
Not in this way.
Had like a design of experiment with repeated measure.
Okay, so you did get that as part of design then.
Yeah.
Okay, was it Ariel?
I had it before with Dr. Tim Ansley.
Okay, so with Tim Ansley, did he tell you there were two kinds of repeated measures ANOVAs? Don't remember? Okay, well, so there are two kinds, so maybe I'll blow your mind and maybe this will be review, but we'll see. I want you to understand the two kinds and how they fit. So, hello. Thank you for typing. Yes, if anybody is shy and they don't want to speak into their microphone, or there's people who are loud in the background, just chat. It's fine. I also enabled live chat on my YouTube page after having so much fun with that in Jonathan's class last week. So you can type on there too. That's why I keep tennising back and forth here. So let's look at the ANOVAs here, and then I'll tell some stories of when people get these confused, because I don't want you to make those same sorts of mistakes. So I am trying to enable, like, I'm not because I'm shy. Okay, fair enough. Technical difficulties is yet another reason why we can use the chat window. Whatever you prefer, it's all good. So let's start on slide 17 here and talk about kinds of ANOVAs. So in the analysis of variance framework, there are really three kinds, two of which would be classified as repeated measures. Here are the things that they have in common. The idea that you must have listwise deletion of missing occasions. That is common to all three of these when you're using least squares estimation. So the problem of how ANOVAs handle missing data is not the ANOVA model's fault. It is the estimation that is the problem. It is least squares. So there is nothing inherently wrong with ANOVA. ANOVA is a choice among many for a particular form of the model for the variance. Another reason, though, that ANOVA is maybe less suitable for some research designs is because there's no means by which to incorporate time-varying predictors. The idea that you can include a covariate to make it an ANCOVA, those covariates are person-level predictors. They are between persons. You can't have a covariate that changes over time. It doesn't work. The other thing that makes this limited is that the ANOVA model fits what is known as a saturated means model, meaning that there are as many parameters as there are occasions. So for example, if I had 4 occasions, the saturated means model would designate one of them as the reference. So let's say time 4 is what it would be in SPSS or SAS. That's going to be my beta 0. And then I would have 3 dummy codes to contrast occasion 4 with the other occasions. So we have 4 betas, we have 4 means. It fits perfectly with respect to replicating the means. So the ANOVA model is saturated means. Now this is all well and good when people show up exactly when they're supposed to. But what if someone comes to time 2 late? What if by the time they get there it's actually time 2.5? Then what? ANOVA doesn't have the capability of addressing that. It doesn't handle unbalanced time. So that's yet another reason why ANOVA may not be suitable for a given research setting. If people follow their own time schedules, then you have to end up rounding time to make it work. So the way that these ANOVAs differ then is what I wanted to talk about today, how they handle dependency. And by handle dependency, what I mean is the pattern of correlation and the type of variance that they allow across time. So it's whether or not the variances across time get to change or not, so whether they're the same or different, and what is the pattern of correlation of the occasions from the same person. That's how these models differ. Okay, you guys with me? Click once for yes, twice for no. This is so weird talking into my basement. I feel like I'm going crazy.
I think I'm able to speak now.
Okay, hello, thank you. Please throw me a bone. I'm so lonely here.
I'm here.
Okay, excellent. Are you ready for this?
Yes.
All right, that's all I need. I need at least one person to be ready. So here is the first one. This is the straw man, what I call a between groups ANOVA or independent ANOVA. I also refer to it in the book as the E-only variance model or between persons model. And this is what we looked at as our first example in the previous example 3A. It's an R matrix that has this form on slide 18. It's known as variance components in SAS. It's known as independent in Stata or identity, I think, in SPSS. But the main point is that it is the general linear model for the variance. All the E's have the same variance across occasions and persons. There is no covariance whatsoever. So it's an independence model. We know that this is going to be way, way wrong for longitudinal data. If you measure someone repeatedly, it's almost certain that there's going to be a correlation between occasions from the same person. This model will also tend to be pretty wrong for clustered data, but less so. Clustered data meaning people who are from naturally occurring groups. People from the same group tend to be more related than people from different groups. And so this model is sort of the straw man is the phrase that I use. It's the thing we know that it's going to be wrong, but it is the worst possible model that you could have. It's where we start. In longitudinal data, we typically wouldn't start here because it doesn't make any sense. I'm doing so just to make the point of how you would actually compare whether or not this is okay to something that has more complexity. So then, the next one, this is slide 19, and this is the one that I thought was just repeated measures ANOVA, the only kind. And this is what we've just been talking about. The idea that the R matrix has this specific form right here, where the diagonal, which is the variation at each occasion, so this would be an example of a 4-occasion R matrix. The diagonal is part within person E, part between person U mean differences, and it's the same all the way across time. The off diagonal is the variance of the random intercepts, where the only reason why there's a correlation or a covariance between occasions is because of this random intercept variance. This form right here has a special name called compound symmetry. And that's the type of variance prediction that univariate repeated measures, that's what this is called, has. So this is one of the options. It's a very restricted option. It can be, it's the most parsimonious model that you would entertain for longitudinal data. So let me ask you a question here. How many parameters do you see in this R matrix? How many different symbols do you see?
2.
2, yeah. And I told you that this is an R matrix that is for 4 occasions, right?
Mm-hmm.
So how many symbols would you see if this was 10 occasions, if it was a 10 by 10 matrix instead?
Still 2.
Still 2, yeah. And so that's why people like this, because it's very parsimonious. The problem is that it's also probably wrong. The only way that you could have the same amount of variation across time is if you had individual growth trajectories that look like this down below, that are parallel. People change the same, they don't spread out, their variability stays the same across time. If people change differently, the variance across time has to change too. So to the extent that you have individual differences in change, to the extent that people change differently, this compound symmetry form can't hold. So then the question is, what do you do instead? So this compound symmetry form is actually a stricter version of what is necessary for this model to give you accurate p-values. The slightly less strict form is something called sphericity. Is this a word you guys have heard before?
Yes.
Yes. Yeah, this is a nice statty term. What I learned about this is to check SPSS output that was like somebody's test of sphericity. And it was like a whole bunch of hyphenated names, you know. I can't even remember them now. Windfelt and Greenhouse Geyser and all these, you know, all these people that made up slightly different versions of this test. And I was told that if that test was significant, you had to look elsewhere on the output for your p-values. And that's about all I retained out of that. Does that sound about right?
That's right for me.
Yep. That's the psych training, still going strong. What sphericity means is that the pairwise differences have equal variance and covariance. It's satisfied by default if there's only 2 occasions. If sphericity is violated, then that's where the different approaches to correct the entire model to make it more conservative come in, corrections with the little E symbol thing. But basically, this compound symmetry model probably just doesn't fit, and you'd be better off with a different one. So the only other option that is available within this world of least squares is the other kind of repeated measures ANOVA. Come back down here. Come on, you can do it. Uh-oh. There we go. Is the multivariate version, or MANOVA, as it is sometimes called. So this type of model is appropriate for longitudinal data or any kind of repeated measures data where you would have like repeated conditions or something like that. It is known as an unstructured model for the variance in mixed modeling terms. That's what we're going to call it. You'll note that there are as many variances as there are occasions. So each occasion gets its own variance. And each possible covariance is estimated separately as well. So the R matrix is symmetric. So like this sigma 2, 1 is the same thing as sigma 1, 2. That's the covariance between occasion 2 and occasion 1. Here's the covariance between occasion 3 and occasion 1, and so on. So in this case, there are 1, 2, 3, 4 variances, and 1, 2, 3, 4, 5, 6 covariances, so 10 possible parameters. Can you guess how many there would be if I had 10 occasions? Chat says, yes, 55. I was going to go with a lot, but yes, 55. And did you use the formula over here to figure that out?
Times 11
Yeah.
divided by 2.
Yep. So this formula may look familiar to anyone who's at SEM. It's the same formula by which you figure out degrees of freedom. It's the number of unique elements in the matrix here. Yep. So that is not a coincidence. This model right here, where you have all possible variances and covariances, coupled with all possible means, which is what all ANOVAs have, this model has a special name in the world of structural equation models. It's the H1. It's the saturated model. So you can think of saturated and unstructured as sort of synonyms. Saturated is what it's called with respect to the means, having as many fixed effects as you have means. Unstructured is what it's called with respect to the variance. So its type equals UN on the R matrix gives you this. So it's all possible variances and covariances. So this isn't really a model. This is the data. There's no prediction here. It's just spitting back what the data want it to be. Each occasion gets its own variance, can't be wrong. Each pair of occasions gets its own covariance, can't be wrong. So when we do model comparisons to figure out whether or not we need something this complicated, this is as good as it gets. Relative to this, everything else is not worse. And so that's where the test of absolute fit comes in structural equation models. It's always relative to this best possible alternative, where we're going to do likelihood ratio tests to see if the fit is not worse. Okay, so here's the summary then. 3 kinds of ANOVAs. They differ in their model for the variance. So we have E only, we have U plus E, which is compound symmetry, and then we have the whatever model. So this last model here, if it's done with least squares, requires complete data. If it's done with maximum likelihood of some kind, it does not. However, what it does require is balanced data. Do you remember balance, that word? It's the idea that everybody shares a measurement schedule. So if we have people who came in at time 1.5 and 2.5 and 3.5, they don't have a place to go in this matrix. So this unstructured repeated measures ANOVA model is only possible when everybody shares the same time schedule. If they don't, you can't do this. And that's why tests of absolute fit are not always available for longitudinal modeling. They're not available when people have their own sets of time equations because there's no single covariance matrix to come back to that's the right answer. Okay, how are we doing, folks? Questions? Okay, do you want to see what it would look like in SAS? Sure, thank you. I appreciate the enthusiasm. Why not? We're all here, right? So I have example 3b. This is from chapter 3 in the book. These are real data. These are data that you will see throughout the semester. It is a real data example of 6 occasions of a response time task that's supposed to measure easy processing speed. And the objective is to see how people change as a function of repeated exposure to this task. So basically, we're just studying practice effects. The idea being that you should get faster at this the more practice you have. And so we'll look at the extent to which there may be individual differences in that tendency. These are data from older adults, so that will be relevant when we start looking at covariates. But for right now, these are just the kinds of ANOVAs and what they look like. So here is the same model for the means. I'm on the page 1 here, where the mean response time at each occasion is going to be perfectly reproduced because what I have is a beta 0, a fixed intercept, which is going to be for time 6, and then I have 5 dummy codes that give me the difference between time 6 and each of the other occasions, and I can work from these 6 effects and get any mean and any mean difference out of it. So in ANOVA terms, this saturated means model has 5 degrees of freedom. The omnibus omnibus test of the main effective time takes 5 degrees of freedom because it's these 5 contrasts that we're testing simultaneously. So that's the same model. What we're changing is the model for the variance. So here we are proc mixed. So response time, RT, is the outcome that we're looking at here. So note that I have this word session. That goes on the class statement and it goes on the model statement. What happens when you put a variable on the class statement? This is analogous to the use of by or fixed factor in SPSS. It's I dot in stata, it's a factor variable in R, it's making the contrast for you. So when I put session on here, it's not going to give me a slope. Instead, it's going to count up how many separate values of session I have and give number of categories minus 1 dummy codes for me. Likewise, session is the variable that denotes which row is which in terms of the rows that come from the same person. Subject equals person ID helps it figure out how to align people into the data set. R and R core is just asking for output so we can see what the form of the model is, the prediction. And type equals VC is the first alternative here. This is my between person ANOVA. So I'm saving the fit statistics from this model into a SAS data set so that I can use them to do math on subsequently. And last but not least, the LS means here gives me this means per occasion. So in terms of reading the output, let me pause. Any questions about the input before we look at the output? Okay. So number of covariance parameters. That's actually parameters in the model for the variance. So it's related to covariance and variance. It's not a good name, but that's what SAS calls it. Columns in X has to do with the number of fixed effects. It should actually be 6, but in this case, the design matrix for the mean differences across time is counting the one that is the intercept, so it's 1 extra. Columns in Z is the number of U's, of which we don't have any, and it tells you how many subjects it thinks you have and how many the maximum observations per subject. So when you're reading in new data, always check these 2 rows to start with to make sure that it understands the structure of your data. It should have the number of subjects is analogous to what's here, and then max observations would be the number of sessions in this case. So here's our first R matrix. This is the general linear model R matrix, independence. So the total variation in response time, this is response time in milliseconds, that's why the number is so big, is the same across all of the occasions, and it'll be across all the persons too. And there's a big empty spot here where there used to be covariances. That's because this model says there aren't any. So it says that the occasions from the same person have nothing to do with each other. So this is as bad as it gets with respect to the model for the variance. Here are my fixed effects. So the last occasion is the reference. So that means at time 6, it takes people on average 1,672 milliseconds to do this task. And relative to time 6, it took them 289 milliseconds more at the first occasion, 143 milliseconds more at the second occasion, and so on. If I want to know if the set of these mean differences is significant, meaning is there a main effective time, that's given to me right here. So the type 3 tests of fixed effects are the multivariate tests, meaning we're testing more than one fixed effect at a time. Given that this is the only thing in the model, this is also the test of the model's R-square that you would get if you were thinking of this in a regression context. And here are the session means, and note their standard errors are all the same. That's because this model assumes the same variability across time. Okay, with me so far? Yep. All right, very clear. All right, you're Good. And if it's not, I literally said the same thing in the book. So you can go back and read almost verbatim probably what I wrote. When I was writing the book, I thought, how would I explain this to people? And I just started typing. So here is the first version of repeated measures ANOVA, the one that I thought was the only version. Univariate, where type equals CS, that's my compound symmetry model. So we are at model 2 here. Now there's 2 covariance parameters, meaning there's 2 parameters in the model for the variance. And those 2 parameters, let me put this together so you can see the full pattern, are given down here, and I colored them blue to make this salient. There's a CS parameter, that's 202677, and then there's residual, which is 34136. Residual is level 1 residual variance. It's the variance of the ease. It's within person. It's intra-individual variation. That's residual. The 202677 then is the U variation. So this is the level 2 between person variance in the mean specifically. It's intercept between person variance. It's all of the variation that's cross-sectional in origin. So if you take this 202677 and add to it this 34136, which we can do because these are orthogonal by definition. There are 2 different levels of the model. The total of them is the diagonal up here in the R matrix. So the total variability at each occasion is this 236813, which is part U and part E. If we take this variance covariance matrix then, which is R, and make it a correlation matrix instead. So we convert these off-diagonal covariances into off-diagonal correlations. We get this correlation of 0.86, which has a very special name. Do you remember what it is? Who's going to answer? Oh, and I have someone else is typing to me on the live thing. Hello.
And from Turkey.
Yes. See? It's an international online course that you've signed up for. You had no idea, right? He says he used ANOVA in his dissertation. You know what? Don't feel bad, because your dissertation is the done kind, and that's all that matters. I have lost count of the number of wrong things that I have in print, or in my master's thesis or my dissertation. Don't feel bad. All we can do is learn more and do better later on. So, meanwhile, I had a question. This 0.86 has a special name. What is it, folks? Yay, ICC, yes, intra-class correlation, that's what it is. So 0.86 then, you can think of it 2 ways. You can think of it as the average correlation across occasions. So note that it's the same value all the way through these off diagonals. It's as if we've averaged across the correlations that would be there. Or we can think of it as the numerator of the ratio of total variance. So 86% of the total variation in response time in this data set is because of level 2 random intercept between person mean differences. Some people are faster than others. That's 86% of the variability here. Meaning that if I had just done a cross-sectional study, I'd still have about 86% of the information. That would probably be depressing in real life, but it is what it is. So why would this matters then if we think about prediction of differences in response time? If we know that 86% is between person, we know we're going to need between person predictors to capture it. Why is it that some people are just faster on average than others? Is it because they're younger, they're more educated, They care more about the task, they're more conscientious, who knows? It's something about the person. That's 86% of the outcome. Something about the occasion, then, is the remaining 14%. So this interclass correlation, even if this isn't the right model, which it isn't, I'll just give that secret away, is a useful benchmark to try and figure out where the action is in your data, how much of it is between relative to within. Okay, with me?
Yep.
Okay, so then there is one more possible model. Actually, no, I skipped over something here that I wanted to point out. So the means are the same. The test of the mean differences now has an F value of 32. In the previous model, it was 4. That's a big difference. If this is your dissertation and you want a main effective time, which of these models are you going to report? The one where it's an F of 4 or the one where it's an F of 32? Yeah. Other than the which one we like better, wouldn't it be nice if there was a way that we could ask which one actually is the better model? We can. That's coming next. But right now we don't have the information in front of us to tell us which of these F's is more believable, the 4 or the 32. What I can tell you is why they're different. So in thinking about what is error, in the first model, error is everything. Everything is E-variance. It's one pile. And so when they're testing all of these mean differences, they're testing them against all of the variability in the outcome. That is after factoring in mean differences on average. That gets you my F of 4. In the U plus E model, the compound symmetry model, now we've split error into two sources, between versus within. In testing mean differences across time, that's within. So only the error that is relevant with the within error is considered error in testing those mean differences across time. That's the 34. In other words, we have just kicked out 86% of the error in testing these mean differences over time, because that source of error is not relevant. Mean differences across time can never explain why some people are just faster than others. They were that way to begin with. And so that's why we end up with this much stronger F, because what is considered error that it's relative to is much smaller. It's only 14% of the noise in the data instead of 100%. Okay. With me, folks?
Yep.
Yep. Okay, good. Questions? All right.
Matt, sorry.
Yeah, please do.
And so I just observed the degree of freedom of the two models. They are different. So the first is like 600, and now for the second model is 500 for the 10 degree of freedom.
Yes. Okay? Yeah, that's because the degrees of freedom method that we're using right now is something called Satterthwaite. It is not the traditional ANOVA degrees of freedom. It starts with that, but then it adjusts it for the relative amount of information across levels on the between level versus the within level. It's analogous to what happens when you have a dependent samples t-test with different group sizes and different group variances. It factors in those differences to what the degrees of freedom should be.
Okay.
So it's not going to be a nice and tidy demarcation of degrees of freedom. The denominator degrees of freedom is, I'm doing this off the top of my head, it's it's going to be, well, I'll just say this rather than give you the math, because that's in chapter 5. The denominator degrees of freedom choices are discussed in there. But this one is going to be closer to the within degrees of freedom, the denominator is, rather than the between.
Okay, thank you.
Sure. So here's the last alternative, the other kind of repeated measures ANOVA that I didn't even know about. That is the multivariate version, type equals UN, which is unstructured. So in this case, because we have 6 occasions, we have 21 possible variance model parameters. That is 6 variances. Here's the R matrix then individual, or shadow that. This model also lets all of the covariances be whatever they want, and the differences between those are more readily viewed as correlations. So if we look down here, this is what the actual pattern of correlation is across these 6 occasions. And it has a pattern to it as well. Not a perfect pattern, but these are real data. Occasions that are closer together tend to be a little more highly related than occasions that are further apart. So the previous model told us that on average, these correlations are about 0.86, but that 0.86 is an overestimate for some pairs and an underestimate for others. So these are the 3 kinds of choices that you have at your disposal in the world of ANOVA. If you use these choices with least squares estimation, all 3 require complete data. We can still use these choices as some of the alternatives in the world of multi-level longitudinal analysis, but by pairing it with residual maximum likelihood, we get the same properties as least squares, but we also can have then incomplete occasions within a person. It will use whatever occasions a person does have to contribute to this matrix. The only thing that is required of this particular model right here is that we have everybody on the same time schedule. Because there's row 1, column 1, that's for occasion 1. Row 2, column 2, that's for occasion 2. We don't have room in this matrix for occasion 2.5 or 3.5 or anything in between. So this is a model for balanced data only. Questions? So now we have yet another F value, 16. So we have Fs of 4 something, 32 something, and now 16. So 3 different answers as to how we would report the omnibus mean effective time. And note, degrees of freedom, very different as well. It's the between degrees of freedom that are being used here, not the within. So which is the right one is an empirical question. To answer it, we have to learn a new technique. If you've had classes that used maximum likelihood before, odds are good you know this technique already. If not, then this will be new. So do you guys know how to do likelihood ratio tests yet? What do you think? Still streaming? Still streaming, good. Hello? Are we still here?
So is that like we have a hypothesis and we have a likelihood for the null hypothesis, and then we have a likelihood for a alternative hypothesis, and then we get the ratio between that two likelihood?
Yeah, yes it is.
I just
Is it like a relative test for how well fits of 2 models
Yes.
compare to each other?
Yep, normally what you end up doing is taking -2 times the difference of the log likelihoods. So you can either divide the 2 likelihoods if it's in likelihood, or you would subtract the 2 likelihoods if it's in log likelihood. The log version is what people typically do because that's usually what gets reported on computer output. So instances in which you may have done this, if you took SEM, this is your chi-square test of model fit. If you did logistic regression and you wanted to test the significance of your model or compare models, that's another likelihood ratio test. IRT, if you wanted to compare like a 1 PL versus a 2 PL, that's a likelihood ratio test. So do any of those sound familiar? Yeah. Okay. So here's what we'll do then. We have a few pieces here comparing models for the variance. Let's take a look at this here. I have the technique in the slides described. It's pretty straightforward. The only trick is to figure out what your software gives you. So we will talk about where this comes from when we get to chapter 5. But on the whole, what you end up with is a summary of how likely your data are given the model parameters. It's going to be based on the concept of height. So the algorithm goes through and tries out different values for all of the model parameters. It plugs your data into a formula. It's the multivariate normal distribution in this case that gives you the height of your data given those parameters. Under the assumption that people are independent, you can take the log of that height and then add them together across people, and the sum of those log likelihoods across people is given as one number in your output. That is the total height of your data for that model. It either comes from maximum likelihood or residual maximum likelihood, or restricted maximum likelihood, same diff. And the question is whether you get log likelihood on your output or -2 times it. The latter is more common in certain programs. So for instance, SAS mixed and SPSS mixed give -2 log likelihood as the summary statistic. So it is -2 times log likelihood, which makes it backwards, such that bigger is worse. So if log likelihood is height, you can think of -2 log likelihood as shortness, lack of height. In other programs, such as Stata and N+, they give you log likelihood directly, so you have to take the -2 part yourself. Either way, it's just the difference. So if you're given -2 log likelihood, it's the -2 log likelihood from the model with fewer parameters minus that of the model with more parameters. So I use those words rather than null and alternative because sometimes the one that you're interested in is the one with fewer, and sometimes the one that you're interested in is the one with more. The order is always the same though. It's the -2 log likelihood from the simpler model, the one with fewer parameters, minus the one with more, because that will result in a positive difference. You then figure out how many more parameters the more complicated model has, so what's the difference in the parameters, and you take that difference in -2 log likelihood, using that degrees of freedom for the difference in the number of parameters, and you compare it to a chi-square distribution. So you can do this in Excel to get the exact p-value rather than looking up all sorts of tables. Stata has a routine to do this for you, and I've given you spreadsheets that you can do this in Excel, and I also wrote a SAS macro, and so that's the last part of this handout, is each of these models has had a table known as InfoCrit saved to it. So let me go back through this handout and point that out to you. InfoCrit stands for information criteria, so it's saving this table right here. It gives -2 log likelihood, the number of parameters in the model for the variance, and then the rest of these things we'll talk about shortly are just variations of -2 log likelihood corrected for the number of parameters and or sample size in the model. So this is the worst model. This is the between person model with one parameter. We then ran the model with compound symmetry instead. That table then for fit looks like this. Note that we have 2 parameters now because we've taken what was just E variance and split it into U variance versus E variance. That has brought the -2 log likelihood down. And then last but not least, the multivariate analysis of variance for repeated measures has 21 parameters and has brought the -2 log likelihood down further. So then I have the results of 2 tests at the very end here, using the macro that I wrote called fit test, which does a likelihood ratio test using those saved tables. So the first one here is comparing the between-person ANOVA to the within-person ANOVA. So the E-only model versus the U plus E model. The difference in the -2 log likelihoods is sometimes known as deviance. So a synonym for this likelihood ratio test is also a deviance test. You can think of it as, deviance is bad, right? So you want there to be less deviance. In this case, a significant result means that the model with more parameters fits better. You could also think of it the other way. The model with fewer parameters fits worse. Likewise, is this model then that has U plus E good enough? That's the same thing as asking, does a model that says the variances are all the same across time and the covariances are all the same across time, does that describe the data sufficiently? To answer that, we compare that model to the unstructured, everything gets to be what it wants model. That is the data. That takes 21 parameters instead of 2, but you know it's going to fit the best. And the fact that the deviance difference here, the -2 log likelihood difference, is 123 on 19 degrees of freedom. P-value that is 0 to the number of digits reported here. It means, nope, univariate ANOVA is not a good fit. And this was foreshadowed when we looked at the pattern in the data revealed by this multivariate unstructured model. The variances decline across time. The covariances, correlations rather, are stronger for occasions that are closer together. They're not the same. So these 2 types of repeated measures ANOVAs, they're very inflexible. The univariate version says everything is the same. All variance is the same, all covariance is the same. The multivariate version says, nope, everything's different. Just as many parameters as it takes to make everything be different. So what we're going to look for are models that are somewhere in between. They're less complicated than letting everything be what it wants, but they're going to fit better than just compound symmetry that says everything stays the same across time. In looking at these sorts of tests, what to do with the significance depends on how you're approaching the comparison. If you're approaching the comparison from the perspective of adding things, so like if I start with my between-person ANOVA model and I add U0 variance, the model can either fit better or not better. If you add parameters, you are trying to improve fit. You are trying to reduce the -2 log likelihood, the deviance. So if you get a significant result, you've made the model significantly better. If you get a non-significant result, you have made the model non-significantly better. If you go the other way, for instance, if I start with the best possible model, the multivariate version of analysis of variance, and I take parameters away, I'm asking if I can simplify without hurting fit. If you're trying to simplify, the simpler model can either fit worse or not worse. So in this case, the simpler model fits worse because it's significant. So this is the chi-square test that shows up in SEM for absolute fit. You're asking, did your factor model fit not worse than the perfect model? The H1. Unstructured in this case. Okay. So there is an answer then in terms of which model is best, and right now of those 3, all it is the multivariate analysis of variance. The rest of these slides talk about ML versus REML. You'll get more practice with that in your next homework. Basically, the rules for model comparisons, if you're using regular ML, you can do any kind of comparison. If you're using REML, you can only compare models that differ in their variances. We're going to be using REML almost exclusively so that we get variance components that are as accurate as possible. So there's more text around that you can refer to in Chapter 3. I try to make it as straightforward as possible. Okay, so questions? Any questions? Now, do you remember why we would do this? Why do we use a model that has more terms in its model for the variance? What's the big picture? Any guesses?
So we have more parameters, so we can reduce the unexplained variance. Is that?
Keep talking. I'm not sure I follow you yet.
No, I just so we now since we have more parameters, so we can model more of the variance in the data, so that we can reduce the unexplained variance in the data.
Not exactly.
Okay.
So the first part of what you said is right. What we're trying to do is find a model that matches the patterns in the data. So if the variances change over time, we need a model that allows that to happen. If the covariances differ over time, we need a model that allows that to happen too. But the process of doing this, though, is not actually explaining variance.
Okay.
That comes next.
Oh.
So explaining variance happens when we put in fixed effects of predictors. Such as the effects. So in this case, the only fixed effects we have are the occasions, whether it's time 1, time 2, time 3. Those fixed effects do explain variance, as would, putting in someone's age or their education or something like that. So we have a question. Except for using log likelihood, can we just use the chi-square difference to model difference? Not sure what you mean. Can you clarify your question? Did I say that right? Oh, yes. So he's noticed something. The output provides, so let me show this to you here. We'll go back up to the top. So the first model has this thing called null model likelihood ratio test. Is that what you were asking me about? Do I understand your question yet? Well, we'll wait for him to answer. I meant to say this anyway, so it's just as well. So this thing does a likelihood ratio test for you of any parameters that you have in the model for the variance besides E. That's what it does for you. Now, sometimes that is a useful thing to know, and sometimes it's not. So when is it useful? When you fit, when we're moving forward, this model right here, this U plus E compound symmetry univariate repeated measures ANOVA model, this thing is going to be where we start in terms of the model for the variance. And now the null model likelihood ratio test piece of output here tests the presence of U0 variance. So you'll note that chi-square of 802 is exactly what I got when I did it myself. That's as it should be. So it tests the significance of the interclass correlation for you, which is helpful in this one case. But if you go down to what the output looks like for the multivariate test, the last model, it has 20 degrees of freedom because there's 20 more parameters besides the E. The fact that 20 as a set is significant to me is not helpful because it doesn't really hone in on which ones are making the model better as a set. So this null model likelihood ratio test is sometimes helpful and sometimes not. Okay, did that answer your question? Yes, great. The procedure, though, this idea of taking this -2 log likelihood difference relative to nested models, we will do that a whole lot. That is how we will test changes to the model for the variance only. Changes to the model for the means, the fixed effects, we will test using wald tests, meaning either the individual tests of each fixed effect that are right here, or testing sets of them as a multivariate wald test. So that greatly simplifies the process of model comparisons. We're only going to need to do -2 log likelihood comparisons when we change the model for the variance. Otherwise, if we add fixed effects of predictors, we will use these univariate and multivariate wald tests to test those instead. That way we don't have to worry about the ML versus REML ways of confusing the results. All right, other questions? Questions from the internet? No more questions there. Questions from you guys? So now you should be able to answer all of the questions on your quiz, and we will go over that in class Thursday. Just to remind you, quizzes get points for participation. So even if you're way wrong, you get your points. Way wrong answers, though, are actually still helpful to me, because if several people have the same way wrong answer, then I know I've misled you somewhere. So the quizzes, the idea is not for you to get out your notes and make sure that everything is perfect. The idea is so that you should... No, we're not doing the answers yet. No worries. We're going to go over the answers on Thursday. But what I'm saying is that what I want each of you to do is to try and answer off the top of your head. That's what I want you to do. If you can't do it, then get out the book, get out your notes, and use those to answer the questions. But these are the quiz questions are hopefully going to be big picture things that you should be retaining between lectures. And if you're not, then it gives you a chance to know what you should be reviewing. And if people have... good, yes, please do. And if people have the same misconceptions, then that tells me what I need to go back over in terms of review as well. So the quizzes are my way of checking in with you to make sure you're getting the big picture things and for you to check in with yourself. So they're low stress. That's the way it goes. All right, so any other questions or things before we adjourn? All right, well, thank you for joining me. I really hope to see you on Thursday, but check your email in the morning just in case. I have no idea what new shitstorm is going to hit us this week. Something between Thursday and Friday last I saw, so we'll see. But I really hope to see you someday again. Until then, stay warm and safe. Bye, everybody.
Thank you.
And I'll be here for office hours if anyone wants to talk to me.